Yeah, I have had a lot of fun this weekend. But look at how cool it looks. I don't know what any of this is. I'm just gonna erase it. So the second major component of machine design, oh, by the way, welcome back. I hope you have had a good morning. Your morning started out by getting to see me, so clearly you had a good morning. Okay. The second major component of this course is designing for failure, okay? Why is failure important? Because quite frankly, your job as an engineer is to ensure a component does not fail. Failure can mean a bunch of things. Damage to a system, which means you have pieces that are not operational. Okay, in a power grid, you have something that's not operational, you don't have power. In an HVAC system, you have something that's not operational, you don't have HVAC, you don't have airflow, you may not have cooling. So you have damage to a system that makes it non-operational. This also means expenses. If something fails, it is always an expense. Sometimes something as simple as having a bolt shear off and then having two components move relative to each other, sometimes that can cost thousands of dollars as people have to go in and inspect every single seam to make sure that the seams are now okay. Inspect to make sure that the movement did not disrupt its functionality. And then they get to it and they find that the bolt is missing and they go, oh, okay, that's where the failure occur. We'll talk about that on Wednesday, Logger. Although we've talked about this already, but we can talk about it on Wednesday in person, or Friday in person. Or you can meet with me separately and we can talk about that. Because we have already talked about both of those in this course. So when you have a failure, there are always expenses incurred. Technicians do not understand how it was designed, so oftentimes they struggle with understanding how to fix it. Now, technicians also do a lot of work studying a mechanism to try to understand potential failure points, those kinds of things. But the burden of failure should be on you to prevent it rather than on them to have to go find it. It is always expensive when they have to go jump in your mechanism, okay? This could also be potentially dangerous. Anytime you have a failure, you could be risking someone's life. Particularly in faster machines, you have to ensure failure is done correctly. And that's why failure is such a major component of this class. I worked with a guy who once told me that he was in a power plant, and this power plant had a giant smokestack that went up. And a team of technicians had gone, climbed to the top of the smokestack, and on their way back down, several of the bolts connecting the walkway to the concrete inside of the smokestack failed. And what ended up happening was about 3 people plummeted 200 feet to their death. And it's one of those things where you don't forget those kinds of moments. When failure occurs, you blame yourself. Even if you went through the process, you feel bad because you recognize Batteries is trash. Doesn't last an hour. That's sad. So I just replaced the battery quick in my camera. Anyways, so to keep going with what I was saying, if somebody gets hurt using your device, you remember it. And you need to do everything you can to try to prevent failure from happening. For many engineers, it's a pressure that's too much. It crushes them. And I hate to think that that's going to be the case. A lot of people will go into manufacturing, not design, just because they don't want to have to deal with the repercussions of what happens. This is also why quality assurance is so huge in most companies. It's because they are trying to figure out potential failure points for mechanisms to ensure that you aren't liable, that nobody does get hurt using your device unless they're being really dumb, okay? I can find, there's 10,000 ways I can hurt myself with a hammer, and have hurt myself with a hammer. But that's not a failure of the people who designed the hammer. That's me thinking I can do everything with a hammer and hitting myself. So when it comes down to it, we have to do what we can to try to prevent failure. First of all, because then it doesn't get caught in quality assurance and quality testing. But second of all, because it is really important because we're dealing with people. We're not dealing with very easy to work with systems. We're dealing with people who have real lives. So that's why failure is important, okay? When it comes to failure, the idea behind failure, a lot of what we talk about here is component failure. But really, failure is at a much larger scale. Failure occurs when a mechanism can no longer perform its function. Okay? This could be because something gets stuck in a gear. This could be because a motor burns out. Failure can occur for many reasons. And all of those reasons you can try to prevent for, you can design it so that no sand gets into your gears. You can design it so that all of your bearings are shielded. You can pick all of these components and design shielding and design casings and really try to make sure that all of these tertiary failure mechanisms don't happen. But on a component level, for components, one of the major things that we don't want failure to happen is you have power transfer. Okay, and then this could be anywhere between a joint to the linkage itself to the next joint. Okay, so like for an example of a gear, you could have a failure where the gear is spinning relative to the shaft, and all of a sudden the gear breaks free on the shaft. So here's my shaft, here's my really poorly drawn gear. Okay, if this shaft can spin and this gear does not spin, you have failure of a component. The failure occurred in the joint. Okay, that's one mechanism. Second mechanism is what happens when failure occurs in the mechanism itself, in the component itself. And here that may be where, if we have a tooth profile like this, okay, if one of your teeth breaks off because it shears, because maybe it's transferring too high of loads, maybe there's fatigue failure there, if that occurs, that this gear may spin without transferring any power, and as soon as that happens, it's now failed. And it could also fail by just the gear cracks, and you have a giant piece of it missing, and that cracked piece then goes into the joint and gums everything up. At the end of the day, though, failure occurs when power is not transferred through a linkage. A gear is a linkage. Failure does not come in. The power does not come in. That's what happens when the connection between the axle and the gear is broken. The mechanism itself cannot handle the power being transferred through it. That's what happens when the component itself fails. And lastly, the mechanism cannot transfer power out of it. If we have the full gear mechanism and nothing is wrong here, but we have components come down into the teeth and jam it up, then we have a failure where power cannot be transmitted out because the joint itself, again, is damaged. So, those three locations, input joint, linkage, output joint, are potential failure mechanisms for every single linkage. And this is, again, one of the reasons why joints are such a major component of design, is because you have multiple ways in which a joint can fail. Which is also why you use standardized components, bearings and gears and all of those, because you can usually have a really good estimate of how it's going to fail and why with those standardized components. All right, so failure occurs when power is not transferred through a component. Okay, now to figure out failure through a component, we need to know failure is going to occur inside of a component when you have a stress that exceeds the yield stress. What does that mean? It means that your component plastically deforms. Your component plastically deforms. Your mechanism was not designed so that your components could be all weird shaped. They all have to be pretty tight toleranced. Okay? You could also fail in fatigue. If you understand the amount of fatigue that is occurring inside of a component, you will need to understand whether or not the endurance limit occurs. Okay? Oh, dang it. I'm touching this board too much. Okay? So first of all, stresses. Second of all, fatigue. And then third of all, deformations. Okay? If you have excessive deformations in an axle, it can cause buckling, particularly if it's in a large amount of compression. It can cause components to skip. If you have a really long shaft and you have a gear right in the middle, the problem is you're going to have a hard time transferring power because the amount of force that is needed to transfer power between those two gears is enough force that it actually causes the shaft to deform up the middle. So if I have a really long shaft and right in the middle I have a gear and it transfers to some other gear chain down here, okay, I may have failure if my bearings are at the end just because the deformation of the shaft is enough that these two gears are no longer in contact when it's trying to portray power. I don't know if you've ever had that happen. It's really annoying. You have to be careful that deformation does not prevent power transfer. And that could be either by components touching each other or components coming out of contact to each other. Or maybe you have enough deformation in let's say you've got two axles like this where you have one large pulley and one small pulley. You have a belt that goes between them. Okay, if the amount of force being exerted on the belt by the belt on this pulley causes the shafts to bend inward like this, your belt is going to go slack. It's not going to be able to transfer power. Okay, so deformations is another big component. You really have to look at all three of these. First of all, whether or not the stresses are low enough that it's going to succeed. Second of all, what kind of fatigue loading is occurring. And third of all, what kind of deformations are occurring in your system as a result of the loading that's being incurred on it. Okay? So, when it comes to determining stresses, we introduced a number of failure determination mechanisms. We talked about maximum shear stress theory, MSS. We talked about the energy theorem, which that gave us von Mises stresses. We talked about Coulomb-Moore. We talked about a bunch of things. What I would like for you to remember most from this course is the von Mises stress. This is it's the deformation energy theorem. I think that's what the D stands for. Don't really remember what the D is right now. But a von Mises stress, the idea behind a von Mises stress is it's represented by a sigma prime, and this is a representative of the stress energy at an X, Y, Z location. Okay? At a very specific point on a mechanism, you'll have a von Mises stress, and that represents the amount of stress energy that is contained by X, Y, Z loading, torsional stresses, shear stresses, bending stresses, axial stresses, all of those. Okay? Von Mises stress takes into account principal stresses. Okay? And if you remember, your principal stresses take into your account your sigma x, sigma y, sigma z, tau xy, tau yz, and tau xz. Okay? All of those 6 components converge to your principal stresses. Now each of those 6 components take into account, can't spell, your bending, torsion, shear, and axial loading. That creates stresses. And each of these comes from individual loading conditions. Understanding what the bending is in multiple directions, understanding what the torsion is, okay? It's very much a process. I drew up this diagram early on in the semester. It's still applicable here. You come up with your loads, okay? This is bending loads, this is shear loads, torsion loads, axial loads. From these loads, you figure out your stresses that are directly caused by those loads. Okay? Once you've come up with these stresses, then you come up with your 6-axis stress conditions. Okay? That's these. Sigma x, sigma y, sigma z, tau xy, tau yz, tau xz. Okay? That's your 6-axis stress conditions. Once you know your 6-axis stress conditions, then you calculate your principal stresses. Once you know your principal stresses, then what you do is you have to rearrange them so that they're ordered. Your sigma 1 should be your biggest principal stress. This is just a simple comparison. Which one's biggest? Which one's second biggest? Which one's third biggest? So that's this step. Once you have an ordered set of your principal stresses, this is where then you figure out your von Mises stress. Try to draw my sigma a little nicer. Okay, your sigma prime, which is your von Mises stress. Once you know your von Mises stress, and you know your material properties, then you can figure out your factor of safety, N. Okay, so this is just for determining a single loading for yield or for ultimate stresses. Okay, now what happens when we get to fatigue? Well, fatigue becomes a little bit more of a challenge. because it takes everything we know about stresses and it makes it worse. Okay? For fatigue, you have to figure out your sigma A and your sigma M, where your sigma A is the amplitude of your fatigue stress and your sigma M is the median fatigue stress. Okay? Both of these are calculated by figuring out what your von Mises stresses are at certain locations. And it's how your von Mises stresses at a certain point on your component shift from minimum to maximum. That determines your sigma A and sigma M. You may have a negative value, you may have a positive value on one side. Your sigma A may be 180-degree reversal of loading. Okay? But again, it comes down to determining your von Mises stress for your component. Okay? Figuring out then what your sigma A and sigma M are. Once you know this, you have to come up with your endurance limit. So all of the process of figuring out your von Mises stress still valid. You use your now 2 von Mises stress, one at your minimum location, your maximum location, to figure out sigma A and sigma M. Here, sigma A is equal to your von Mises minimum plus your von Mises maximum divided by 2. I believe that's... Nope, that's sigma M, sorry. Sigma A is max minus min over 2. Okay? Use those formulas, you figure out sigma A and sigma M. You find your endurance limit, and then you plug it into your stress condition to figure out M. Okay? So even more steps involved because you have to do this twice now. Figure out sigma A, sigma M, figure out SE, figure out your M. That's what. Knowing what your factor of safety is, you want a large factor of safety to ensure failure does not occur. Okay? Particularly if you're not very comfortable with how you defined your loading conditions. If your loading conditions could be larger, you may have to increase your safety factor because you're not sure of how much larger your loading conditions could be. Usually when you're designing for maximum loading conditions, not like, well, you know, 50% of the time I'll have about this loading. No, you design for worst case scenario because every once in a while when you hit that worst case scenario, your machine is going to have to be able to handle it. Okay. Lastly, discussing deformations. What I suggested in this class is use SolidWorks. Use finite element software. For linkages that are very, very simple, you can calculate the deformations, but you shouldn't. Because it's a lot of work, and quite frankly, the hand calculations that you come up with, nobody does that in industry. Everyone uses finite element simulations, which is one of the reasons why we use them so extensively in this class. All right, I will see you in class. If you do have questions on power transfer, that was the force being transferred through component. And if you do have questions on spring selection, you can come talk to me, set up a time to meet. We can figure that out. We can talk about that a little bit in class on Wednesday and Friday. Otherwise, this is the last lecture that I was planning on giving that's pre-recorded. I'll see you in class, and then I will see you on Zoom for your final presentations. And that's it. Have a good rest of your day. I miss you already. And I'm going to talk about machine design for another long while.